This is the third video for section 1.1 Rosen, Discrete Mathematics and its Application. We just got through discussing the logical connectives for propositions to create compound propositions. And now we'll discuss the use of truth tables. We saw a little bit of truth table use when showing the truth values for the different connectives. But we can use them to do a wide variety of analysis of compound propositions. But first, what we have to do is identify how many rows we need. And when we're constructing a truth table, we're going to basically need a row for every possible combination of values. And if there's one proposition in it, there's only two possible values, true and false. But if there's two propositions, each of those could take on two values, and so we'd need 4 rows. And if there's 3 propositions, we'll see that we'll need 8 rows. And then the columns, each column will need for the atomic proposition, but then we'll use columns to do smaller sub-compound propositions, and then the last column will be the overall compound proposition that we're interested in. And then in a separate video, I'll do a shorthand approach for a truth table. All right, so here's a compound proposition. It reads P or Q implies the negation of R. And since we've got 3 atomic propositions in this compound proposition, we're going to need 3 columns to capture all of them. And you can see that we'll need 8 rows to get all possible truth values. And the way we construct that generally is for the leftmost atomic proposition, we would say true, 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 false, 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 false. And then the next one over, true, true, false, false, true, true, false, false. And then the last one will just be true, false, true, false, true, false, true, false. And that way we can ensure that we're getting all possible values of the atomic propositions. And so now what we're going to do is create a intermediate columns for for some internal compound propositions. We'll do a column for the negation of R and a column for P or Q. So for the negation of R, you can see that it's just going to be the negation of every value of R. So if R is true, false, true, false, true, false, then the negation of R will be false, true, false, true, false, true, all the way down. P or Q is a straightforward application of the connective. So remember, for the disjunction, only one of them has to be true. We look over here and we see that P is true and Q is true, therefore P or Q is true. And for the second column, they're both true, so P or Q is true. The third column, P is true and Q is false, but for disjunction, that's enough to make it true. And only where Q and P are both false are P or Q both false. Oops. Sorry, just clearing the markings. Okay, and now that we have these 2 intermediate columns, we can do the implication in this last one, which will be the last step. And I have the hypothesis on the right and the consequence on the left. So that's the direction we'll look at it. Well, this first one we could see is false because the hypothesis is true, the consequence is false. When that's the case, then the implication will be false, and we see that that's true. That's correct. Correctly entered. When they're both true, the implication is true. Also note down here that when the hypothesis is false, the implication is true. That's the vacuous case. And a couple of more have the implication being false when P or Q is true and the negation of R is false. So for this truth table, this is the resulting possible truth values for various inputs, all possible inputs of P and Q. Okay, we'll do a shorthand version of this later. We can also use truth tables to show that two propositions are equivalent, or two compound propositions are equivalent. I had stated earlier that the um, contrapositive is equivalent to an original implication. Well, let's show that using a truth table. Here we have the original implication. Here we have the contrapositive of it. And we have two atomic propositions P and Q, so we only have 4 lines. I capture the intermediate values of the negation of P and the negation of Q. And then I just apply the definition of the implication here to get true, false, true, true for these truth settings for P. But note that for the negation of Q and the negation of P, since that's false, that's going to be true by the vacuous case. If the negation of Q is true and the negation of P is false, that's going to be false. And then if the negation of Q is true and the negation of P is true, that's also going to be true by the vacuous case. And the negation of Q being true and the negation of P being true gives us true as well. And then note that these two columns have exactly the same truth values, the same order for the P and Q inputs. So that proves that P implies Q and its contrapositive are equivalent statements. We can also show non-equivalence. So we said that the converse and the inverse were not equivalent, and I have those listed here. So here we have P implies P and Q, all possible values. Negation of P and negation of Q as intermediate columns. Here's the original implication. Here is the converse on the right and the inverse in the middle there. And note that they do not have the same truth values, so they are different than the original implication. But you can also note that this is the converse and the inverse have the same truth tables, so they are equivalent to each other. All right, a couple more slides. How many rows are there within propositional variables? Well, for 1, we saw that there are 2 rows. For 2, we saw that there are 4 rows. 3, we saw that there are 8 rows. Turns out it's 2 to the n. So if you have n propositional variables, you're going to need 2 to the n rows to capture all possible values. So these tables can grow pretty quick. And then finally, we have the precedence of logical operators. We'd seen earlier that P or Q implies a negation of R, that the implication was applied last. So that's because the negation is the highest priority of precedence, then conjunction, then disjunction, and only then do we do implication. So we could use parentheses to force the ordering, but we didn't need to because implication is done last. But if we had intended P or the result of Q implies not R, we would need parentheses to do that. Okay, that concludes this presentation. I will have one more video showing the shortcut procedure for truth tables.